Hello. In today's discussion, we will be revisiting a topic we have previously studied, the motion of a body thrown at an angle to the horizon. Our objective for today is to provide an explanation of how the trajectory of this body appears, while also presenting the equation that represents this trajectory. Let's begin by examining the scenario where a specific initial velocity is given to the object when thrown at an angle. As we know, there are two parts of this trajectory, i.e., there is a definite ascent and then descent of this body. In this particular situation, we observe that the motion occurs on a two-dimensional plane, specifically the y-ox plane, where O represents the origin of the coordinate system. By analyzing the shape of the trajectory, we can deduce that it could potentially be a segment of a circle, a segment of a sine wave, or even a different type of curved line. Our objective is to determine the exact nature of this trajectory and acquire its corresponding equation. How can we accomplish this? Well, we must first recall how the movement of an object along the x-axis and y-axis is typically described. It is important to remember that there is a gravitational force, known as the acceleration of free fall, which acts vertically in a downward direction. There is no acceleration along the horizontal axis, so we can recall that this movement is uniform. Therefore, the equation of the x-coordinate will be described as the equation of uniform rectilinear motion. So, now let's write it down. In order to find this coordinate, we multiply the projection. Velocity on the x-axis is multiplied by the flight time, i.e. v initial cos alpha times t. Here we see that there is no component that is responsible for the accelerated motion, so we leave the equation in this form and we take the initial coordinate of this body as 0, given that at the moment of throwing the initial coordinate coincides with the beginning of this motion. In the same way we write down the equation for the y-coordinate. Here the equation of motion of the body with acceleration will already work. And we also need to know the initial velocity, or rather its projection on the y-axis. So we need that component. And the equation that we can write down will already look like v initial sin, a multiplied by the time of flight and minus, is exactly the component that is responsible for the equivariant motion of this body. So, we have received two equations, each of which answers and describes the dependence of the given coordinate on time, that is, both of these quantities are tied to time. In order to obtain the equation for the trajectory, what actions can we take? It is important to understand that the equation for the trajectory represents a line in the coordinate plane, specifically in the y and x coordinates. Our objective will then be to create an equation that demonstrates the relationship between these coordinates of one coordinate on the other. That is, how the y-coordinate behaves as the x-coordinate changes. This is our main task in this case. Therefore, we need to solve the resulting system of equations. In order to establish a relationship between the y-coordinate and the x-coordinate, we need to eliminate the variable of time. Both equations involve time, so our approach will involve expressing time using the x-coordinate. By substituting this expression for time into the y-coordinate equation, we can eliminate the dependence on time and establish a connection between the y and x coordinates. To accomplish this, we'll calculate the time in the first equation as the ratio of the x-coordinate to the projection of the initial velocity on the corresponding axis. Let's now proceed with this mathematical operation to remove time from the equations. And now we can substitute this expression into the corresponding points in the y-equation. So we get that here is the product of the initial velocity by the sine of alpha. Then we multiply by time. This is x divided by initial velocity by sine alpha. So, and accordingly we're left with the second block of this formula, We take the g in half forward and we are left with the square of this expression. So, we have obtained an expression that already connects the y-coordinate and the x-coordinate, and here we can carry out a certain simplification. We see that the initial velocity in this part of the equation is reduced. And here appears the ratio of the sine of alpha to the sine of alpha. This, I remind you, is the tangent of alpha. So let's rewrite this expression. Let us put x forward. Here we have the product of the tangent of the given angle, minus. Here we see that nothing is simplified. That is the only thing we can put forward is this coefficient, which will be some constant, because the acceleration of free fall, the initial velocity for the given throw, the cosine of the angle for the given throw, these are all constant values in this case of motion. So we can write it down as some coefficient in front of the variable x. And multiply it by x squared. What we have gotten with you is the equation of the relationship between the y-coordinate and the x-coordinate. As we can see, time has been removed from the equation, which is what we were aiming for, and now we can draw a conclusion as to which line will describe the trajectory of the motion of this body. If we look carefully, we see that we have here the x-coordinate, which is an independent variable in the first degree, and also the x-coordinate in the second degree. That is, I can rewrite this equation in the form minus the x-coordinate squared times some coefficient, which let me denote by a letter. Then, the coefficient in front of x will denote by the letter b. That is the engine from this corner. Let it be the letter b. And accordingly we get plus b times x. So we see that by simplifying this notation a little bit, we get the equation of a parabola, which is the quadratic dependence of the y-coordinate on the x-coordinate. Please take into consideration that the presence of a negative coefficient in front of the variable x indicates that the branches of the parabola are directed downwards. This indicates that the parabola is in a reoriented state, a phenomenon that is consistently observed in everyday motion. As a result, this equation proves to be valuable when solving problems related to determining the position of an object based on one of its coordinates. For example, if we are dealing with a motion that involves an initial velocity and a throw angle, we can easily establish the relationship between the two given coordinates by using the appropriate coefficients derived from this equation. The practical applications of this derivation are wide-ranging and enable efficient problem solving in various situations. And so we will see the solution to the problem in practice. See you later. Goodbye.